Hello everyone and welcome back to Unit 4, Matter and Energy. Today we'll be talking about the last topic in this chapter, which is heat equations. So basically you guys will be able to calculate the heat energy and some other constants in the heat equations which are given in table T, and then we'll also be using some factors that are given in table B, which means you need your reference table packet for this topic because we'll be using the two tables, table T and table B. So just a quick review. We talked about the exothermic and the endothermic reactions. So we said that endothermic reactions are the ones that absorb heat. So basically when heat enters in the system, so if you're looking at a reaction that involves converting a solid into a liquid, liquid into a gas, or solid into a gas, so that forward reaction, all of these reactions will need energy. They will absorb energy from the outside. So the energy or the heat will be entering into the system. So they will be the endothermic reactions. Exothermic reactions, on the other hand, are when heat is released from the system. So heat exits the system. So if we are looking at any reaction that involves converting a gas into a liquid, liquid into a solid, or gas into a solid, so that backward reaction, all of these reactions will release heat. So they will be the exothermic reactions. So when we talk about energy in terms of chemical reactions, exothermic reactions will happen when we are combining two things to form one bigger thing. So let's say this is what the equation looks like. Let's say you have a substance A and you have a substance B. You are combining both of them to make a substance C. And during this process, while you're doing that, some heat energy will be released. Now, because that heat energy is being released, you have that as your product. It will be on the product side in your equation. Endothermic reactions, on the other hand, are when you have one thing and you are breaking that one thing into two or more smaller things. So that type of reaction will require energy. You will need some sort of heat energy, some sort of force to start that breaking process for this one substance. So let's say you have this substance C, you will provide that with some heat energy, so that substance C will break down into substance A and substance B. So a quick way to remember all of this is BARF, which means break, absorb, release, form. So if you are breaking one thing into two or more smaller things, then energy will be absorbed in order for that one thing to break. So this is going to be an endothermic reaction. But if you are forming a bigger thing with some smaller things, then energy will be released during that process, and that's going to be an exothermic reaction. So now if you guys look at table T in your reference table packet, you are given some equations for heat. So these are the three equations that you are given. Let's start with this first equation right here. Q equals mc delta T. In this equation, Q represents the heat energy. And the unit that we use for heat is joules, which is represented by J, an uppercase J. Please do not use a lowercase j. The second constant that we have in there is m, which is mass. And as we all know, the symbol for mass is, the unit for mass is grams with a symbol G. Next thing that we have in there is the specific heat. So specific heat is the amount of heat that we need to convert 1 gram of to change the temperature of 1 gram of something to 1 degree Celsius. So that's a fancy definition there. For example, the specific heat of water is 4.18 joules per grams degrees Celsius. What this means is that if you have 1 gram of water and you want to raise the temperature of that 1 gram of water to 1 degree Celsius, you will need 4.18 joules of heat energy. That's what the specific heat means. Now, do you need to memorize this specific heat for liquid water? Nope, because it's given to you, and I will show you guys in just a bit where is that this amount given. So the next thing that you have in this equation, the last constant, is delta T. So this delta, wherever you guys see the delta symbol, that always represents a change. So in this case, it's delta T, so that represents a change in temperature, which means whatever your final temperature is minus the initial temperature. So initial is whatever you start with. Now, one of the most important things related to this topic that you need to keep in mind is that when you use any of these three equations to calculate the heat energy, you get the value for your Q. If that value turns out to be negative, then that means the reaction, whatever reaction you are looking at, is an exothermic reaction because it has a negative heat energy. Because that negative heat energy is telling you that heat is being released. If the value of Q that you get is positive, then that will represent an endothermic reaction because it will indicate that heat is being absorbed by the system. Heat was added into the thing in order for the reaction to get started. So that's one thing to keep in mind. Now, if you look at the other two equations for heat that are also given in table T, so that's Q equals mHF and Q equals mHV. For in both of these equations, once again, Q represents heat, and then M is the mass, HF is the heat of fusion, which is the heat energy that is required to freeze or melt something, and then HV is the heat of vaporization, which is the heat energy required to boil or condense something. So make sure you guys know what both of these types of heat means. Now let's turn to the first page in your reference table packet. That's where you guys have table B. And table B has some physical constants for water. And here you guys see the heat of fusion for water, you have the heat of vaporization for water, and you have the specific heat for water. So this is the number that I was talking about a few minutes ago. Okay, so if you guys are ever given a question on Regents exam, and you have to use any of these three numbers for water, they will not be given in the question because you guys will be expected to know where to find the heat of fusion, heat of vaporization, and specific heat of water. So that will be in table B. So now let's look at some of the problems. Let's try to solve some problems using these heat equations. So question number 1, you have to calculate the amount of heat that is required to raise the temperature of 15 grams of water from 20 degrees Celsius to 50 degrees Celsius. So the first thing that we want to do is see what are some of the things that are given. So we are given the initial temperature, which was 20 degrees Celsius, and the final temperature, which was 50 degrees Celsius, which means we can go ahead and find delta T, which is the change in temperature. So we'll just do the 50 degrees Celsius because change is always final temperature minus the initial temperature. So we'll do 50 minus 20, we'll get a delta T of 30 degrees Celsius. Next thing that's given is the mass, which is 15 grams. So all we have to do is find the amount of heat that is required. And remember that this question is for water, and we already know the specific heat of water from table B. So we can just go ahead and use the equation Q equals mc delta T. We plug in all of the numbers, mass of 15 grams, specific heat of 4.18 joules per grams Kelvin, and remember we got this specific heat from table B, and temperature of 30 degrees Celsius. Now, there is a problem here, and that problem is that the unit for temperature that you are given in this value for specific heat is in Kelvin. But this temperature that we have right here is in degrees Celsius. We cannot have two different units for the same quantity, for the same property. So we will have to convert this degrees Celsius into Kelvin. So remember that we are given the equation to calculate the Kelvin temperature into Celsius temperature, or Celsius temperature into Kelvin temperature in table T. And this is what the equation looks like. K equals whatever temperature you have in degrees Celsius plus 273. So in this case, we have 30 degrees Celsius plus 273, and we will get our temperature in Kelvin to be 303. So now we can go ahead and plug that into our equation, and we'll just do the multiplication to get our final answer, which will be 18,998.1 joules. Now, another thing that you can do is that you can go ahead and convert this, simplify this, and convert this into scientific notation. So before we get to that, how did we get this joule? Well, we simply just canceled the grams with the grams, and we canceled the kelvins with the kelvins. So the only unit that's left is joules. So now if we convert this answer into scientific notation, I just moved the decimal 3 times to the left, and that gave us a power of 3. So if you look at your prefixes reference table, 10 to the power of 3 is represented by a prefix kilo. So your final answer will be 18.9981 kilojoules. And again, the question is not asking for this step, so you don't have to. But this was just an extra quick review for you guys if the question is ever asking you to do that. Here's another type of question. When 20 joules of heat are added to 2 grams of water at 15 degrees Celsius, the temperature of the water increases to. So now let's see what's given. We are given the heat, which is 20 joules. We are given the mass, which is 2 grams. We are given the initial temperature, which is 15 degrees Celsius. But remember, once again, we will have to at some point convert this degrees Celsius temperature into Kelvin. So why don't we go ahead and just do that now, really quickly. So once again, table T has given us the equation. K equals temperature in degrees Celsius plus 273. So we'll do our math to get the temperature in Kelvin to be 288 Kelvin. Now what we have to find, the thing that's unknown that the question is asking us to find, is the final temperature. So we'll use the same equation, Q equals mc delta T, and we'll start plugging in the numbers. So we'll say that heat is 20 joules, the mass is 2 grams, we know the specific heat of water is 4.18 joules per gram Kelvin, and we don't know what final temperature is, so that's going to be X minus 288 Kelvin. So now we just do some basic algebra. And what I can do is I can bring this whole quantity, this whole thing that is being multiplied by this number, I can divide that on both sides so that it can go to the other side. And then I can add the 288 Kelvin on both sides so that it can be canceled out on this side. So when we do all of those steps, this is what our equation will look like. So we'll have 20 joules divided by this quantity, 2 grams times 4.18 joules per gram Kelvin plus 288 Kelvin. So now on the other side of the equation, we'll only have X. But when we do all of this math, our final answer will be 290.4 Kelvin. Okay, now if you, and that's going to be our final temperature. Now, if you might want, you can also go ahead and convert this temperature back into degrees Celsius using the same equation, but this time you'll just have to rearrange that. And so we'll do 290.4 Kelvin minus 273, and your answer will be 17.4 degrees Celsius. Okay, now another type of question that you can get is when 50 joules of heat is added to raise the temperature of water from 5 degrees Celsius to 15 degrees Celsius, what's the mass of this water? So once again, we start with what's given. We know the heat is 50 joules, the initial temperature is 5 degrees Celsius, and the final temperature is 15 degrees Celsius. But once again, we'll go ahead and convert our degrees Celsius temperatures into Kelvin. So when we do that for both of them, we use the same equation from table 2, which is K equals degrees Celsius plus 273. So now our initial temperature is 278 Kelvin and the final temperature is 288 Kelvin. The unknown is the mass. That's what we have to figure out. We'll use the same equation, Q equals mc delta T. We'll start plugging in the numbers. Q is 50 joules, mass is unknown, so that will be X, and then the C, which is specific heat of water, is 4.18 joules per gram Kelvin. The delta T, or change in temperature, will be your final temperature, 288 K, minus the initial temperature, 278 K, and which is going to be a difference of 10K. So now we'll just go ahead and bring this whole thing. So we'll just divide this whole thing on both sides to get 50 joules divided by 418 joules per grams Kelvin times 10K. And when we put that in the calculator, we'll get a mass of 1.196 grams. Okay, another type of question that you can get is how much heat energy is absorbed when 10 grams of ice melts to form liquid water at the same temperature. Now let's start with what's given. You are given the mass of 10 grams. And we know, because we are talking about the melting of ice, that means we are talking about the heat of fusion. And if you look at table B, the heat of fusion for water is 334 joules per gram. You have to find the heat. The equation that we use for this question will be Q equals mHf. We'll just plug in the numbers. Mass is 10 grams and heat of fusion is 334 joules per gram. And then we'll just do the calculation, put the numbers in your calculator to get the heat energy to be 3,340 joules. So how did we get to those joules? Well, we just cancel the grams with the grams. The only unit that's left is the joules. Finally, the last type of question that you can get for heat equations could be how much heat is absorbed when 70.0 grams of water is completely vaporized at its boiling point. So once again, look at what's given, the mass of 70.0 grams. And because we are talking about the vaporization of water, so we know we have to look for the heat of vaporization of water in table B, which is 2,260 joules per gram. You have to find the heat energy. So the equation that we'll be using is Q equals mHv. Just plug in the numbers. Mass is 70.0 grams. Heat of vaporization is 2,260 joules per gram. Do the math. We get an answer of 158,200 joules. How did we get joules? Well, grams cancel out, and that's how we get to the joules. You guys can also go ahead and simplify this and convert this into kilojoules. So all that we have done is move the decimal 3 times to the left to get a prefix of kilo, so which is 10 to the power of 3. So that is it for your answer. So that's all for this chapter. We are officially done with Unit 4. So I'm going to peace out with that, and we'll see you in the next one.